Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
University of Virginia. Kevin is certainly no stranger to this part of the world. He got his Ph.D. from the University of Washington and has visited us a number of times. Today Kevin's going to come and talk to us about aspect-oriented programming, or whether we really need aspects for aspect-oriented programming. So, as is typical, Kevin is ripping off his Ph.D. students' excuse me, work. No, I'm just kidding. Kevin.
Thanks. Thanks. Yeah, you know, it's the price of doing business with faculty members to have them rip off.
You pay them, so they
Good. Good. So this work really comes out of a mostly National Science Foundation funded effort to try to understand this phenomenon of aspect-oriented programming. It's an interesting area because, you know, there's a lot going on, conferences, substantial industry buy-in, and so on and so forth. There's some things that are evidently not right about the story we're being told, but then there's some other stuff about it that's pretty interesting. So the NSF basically hired me and my colleague Bill Griswold at UCSD to, you know, try to sort it all out, and that's what we've been looking at. So all of this work really centers around the issue of modularity in design. That is the fundamental issue, and of course, this topic goes way back to Dijkstra's notion of separation of concerns, to concepts of abstraction and information hiding, and so on and so forth. And the story that the aspect-oriented programming folks are telling really centers on improvements in our ability to design software with respect to these concerns, with expected payoffs in terms of improved understandability and trustworthiness, parallel development, time to market, ease of change, giving us the ability to produce more variety in our software at less cost. So the story that we're told by the aspect-oriented community is that our prevailing approaches to separating concerns, to modularizing designs, really are inadequate. By prevailing design approach, we generally mean those approaches that are roughly object-oriented in one way or another. We're talking about objects, components, web services, all of these sorts of approaches that center on, you know, APIs. The story is that modularizing systems in this way is inadequate for separating out some important concerns that arise in practice and that arise increasingly in the kinds of systems that we're trying to build today. And that the consequence of these inadequacies is that we end up with poor modularity. And in particular, we hear these terms fragmented and scattered and tangled code. So I got interested in this area because, A, it's influential. There's significant research going on. There's lots of industrial buy-in at this point, significant endorsements from places like IBM. It's hot in the developer community. On the other hand, it's a controversial area. Early projections of benefits were really quite unrealistic. You know, one joke goes that you write your base code and then you write pound safety, and suddenly, you know, you have safe base code. In other words, you add a safety aspect for safety or add a security aspect for security. Those projections probably were overly optimistic. AOP also kind of questions some tenets of good software design. In particular, it tends to violate modularity and abstraction in some important ways, and it challenges certainly, or can challenge, our ability to reason about the behaviors of the systems that we build. So the kinds of problems that we see in current aspect-oriented languages are these, and I'm just going to review them really briefly. We look at aspect languages today. We find programming models that we believe are overly complex, leading to program designs that are overly complex. System architectures are overly constrained, which is to say you can only build aspect-oriented systems in certain ways today. And those are the problems that I intend to talk about addressing today. So the rest of this talk is structured roughly as follows. For those who are not kind of in the know, I'll briefly give you the story on what AOP is for. a brief introduction to AspectJ, which is really by far the most influential model of aspect-oriented programming today. And then I'll identify a couple of key problems with the AspectJ-like model and tell you about how we solve them. I'll identify a couple of important asymmetries in the design of the AspectJ language model, show you how they lead to some problems in terms of our ability to separate certain kinds of concerns, and how they lead to fragile and overly constrained structures. And time permitting, I'll get to this last question: what about obliviousness? Obliviousness being a term that arises frequently in the aspect-oriented world. Yeah?
Just sort of as a high level, does aspect-oriented programming assume that object-oriented programming is sort of, the right model and build on it? I mean, is there a way to separate the two, or are they completely, connected?
Let's see. In principle, there's not that assumption, but in practice, there is that assumption, which is to say that almost all of the work going on in that community assumes an underlying object-oriented model. Certainly, AspectJ and all of the languages that are like it assume an object-oriented model and then basically add some reflective stuff on top that allows you to refactor things in certain new kinds of ways. So I think for all practical purposes, it's reasonable to basically say it's an extension of the OO model. Okay? So first section of the talk, what is AO for? The basic notion is that when it comes to implementing certain kinds of concerns in software, like an execution tracing policy, or cross-module optimizations, or use of thread pools, or security policy enforcement, or code to integrate the behaviors of separate components, that we often end up with code that looks like this, okay? Where there's some kind of base code, that's the black code to do what you want to get done, and then there's some scattered around bits of blue code to accomplish or to implement these other concerns. If, for example, you want to do procedure call tracing, it would be very common to include code all over the place to output trace messages. That would be the blue code. The problem is that now when you want to change the policy for how you trace procedure calls, changing the selection of calls to trace, for example, you may need to dig up lots of code in order to make those sorts of changes. So the consequences of this kind of scattering and commingling of code for cross-cutting concerns is expected really to lead to bad consequences in terms of more faulty software, broken deadlines, and increased costs to build and change systems. So AOP fundamentally claims to provide improved abilities to modularize code, and in particular to modularize the kind of blue code that tends to be scattered around a system if one is using a straightforward object-oriented approach. Okay? So AOP, going to your question, generally extends object-oriented languages with new mechanisms to allow for modularization of cross-cutting concerns. So that really is the kind of key phrase at the heart of that community, to enable better modularization of cross-cutting concerns. And the way that it works is to allow, in some sense, for one module, the module that's going to hold all the blue code, in some sense to modify the behavior of other modules in the system in potentially very intrusive ways. Okay? So that's where some of the controversy arises. So the idea then in AOP is that instead of writing code that looks like this with the blue stuff all over the place, using these new mechanisms, you want to write your code like this. The black code is generally referred to as base code. The blue code is now modularized, localized in one place, and is referred to as aspect code.
So let me just be straight. So when you say modular, you mean basically what you just said. It's localized in one place, not that it's self-contained or provides an abstraction of a module in the classic sense.
Well, at a minimum, that it is textually, lexically, in terms of the physical architecture, localized in one place. Now, you'll get arguments as to whether aspects support abstraction. Take logging policy, for example. You have a policy for which execution events in a program you want to log. If all of the code that sort of implements a particular policy is localized in one place, then in fact that module could be claimed to abstract the logging policy.
But in some sense, then it destroyed the modularity of the other things because they're not localized in one place anymore.
It destroyed the modularity of the other stuff?
The base code, because you can't look at the base code and see what's in that module because there's stuff off to the side.
Aha, so by removing the blue code from the black code, you make it harder to understand what's going to happen in terms of the execution trace when the black code runs.
Right.
Yeah, that's right. That's right.
But we do that all the time when we factor out procedures or refactor class hierarchies or any other time, pull out some piece of code that might be called implicitly or explicitly.
Right, I'm just trying to understand what the word modularity means in this context, because it seems like there are a couple different senses.
Well, I mean, it's an excellent question, right? I mean, because one notion of modularity is just lexical. Another notion of modularity has to do with the design process, that different teams can be responsible for developing different pieces of a system and for doing it relatively independently because there's some kind of agreement that decouples them and that guarantees that their resulting bits of code will integrate. I'll get back to that later. And then there's sort of semantic notions of modularity in terms of ability to reason about what happens based on some local piece of code. So, you know, the answer, I think, to your question is it depends, you know, exactly which form of modularity you're talking about.
I guess, you know, in some sense, you know, following Jim's question, I'm thinking, you know, does it affect my ability to reason about, you know, broadly across the system, you know, what's happening? And you know, in other words, each module will have this extra thing you have to look at. So,
Sure.
So has it really changed globally the notion of what you know what you need to know to reason about things? It seems like it hasn't decreased. I guess when I think of abstraction, I think of decreasing complexity. Right? I need to know less to you know. I need.
Okay. Well, I mean,
hidden.
so the claim is that the people who are writing the black code do in fact need to know less, because the people who are writing this module here, they don't necessarily want to know what somebody else's policy is for how execution of their code is going to be logged or traced. Okay? So to the extent that they can forget about
they
it.
can successfully do that. I guess that's the question.
That is the question.
Right.
That really
Right.
that's really the heart of the matter, and I'll come back to that again at the end of the talk. Okay? So that's the goal of aspect-oriented programming, to allow that kind of modularization. And the way it happens is that code in a third module can, in some sense, intrude into the behavior of other pieces of your system. So the next part of the talk here is a kind of an introduction to AspectJ. And really this is meant to give you a clear sense of the mechanisms by which this new kind of modularization becomes possible. So there are 4 key mechanisms that you have to understand really to have a reasonable sense of what AspectJ is about. Join points, point cuts, advice, and finally aspects. An aspect is a particular kind of module, okay? So join points are points in program execution where you might want one of these third-party aspects to come in and change the behavior of that would happen otherwise. Point cuts are essentially predicates that serve to pick out subsets of join points. Okay? So I could, for example, write a point cut expression that picked out all calls to all methods within some piece of my system. Or I could write a different point cut descriptor that would pick out all calls to all methods whose names start with set. That would be a different predicate picking out a different set of join points. Okay? Advice is essentially an anonymous procedure body, and the idea is that you're going to take one of these anonymous procedures, or advice, and bind it to all of the join points that are picked out by a given point cut descriptor. Okay? So AspectJ allows you to say, here's a predicate that picks out all calls to all methods in this package that begin with the word set. Point cut descriptor picks out a set of join points. And then within an aspect, you can say, at each such join point, I want the following piece of code to run. Okay? So at any call to any method within this package, run this code that outputs a message saying this procedure was called, for example. That would be a way of, in a local, lexically local way of implementing a particular policy about how to trace procedure calls in a piece of a system. Finally, then, an aspect is a class-like module that in addition to doing what normal classes can do for the most part, within which one can also declare point cut expressions and bind advice to join points. Okay, so an aspect is like a class, except that it can do these other, it can do some of these other advising activities. And the notion of AOP then is that in order to modularize cross-cutting concerns, you write aspects.
What is the advice? Is that code? Does it execute?
Yes, it's code.
So it's code that speaks about the lexical structure of the code that it's modified of the join point.
Yeah, I'll give you a concrete example, Rob.
Well, I don't want to interrupt your concrete example, but I had a more general point that I'm hoping you're going to get to, because it's one of my confusions about aspects, which is aspect-oriented programming inherently metaprogramming? It seems like when I'm trying to isolate design decisions that are about the problem to be solved, that's where your classic Parnas modules come in. And it seems like this new kind of modularity that we're trying to achieve somehow seems to be inherently about the program itself and not so much about, the solution to customers' problems, right? Like the classic examples always tend to be things like, logging, error handling, blah, 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 but, I can't even tell you what the decision is without talking about there being a program and what I'm going to do to the program.
Yeah, I'll let the cat out of the bag a little bit. I mean, I think the answer to your question is no.
Okay.
Although it's usually talked about in that way.
Okay.
Okay? But really, when you get right down to it, what you have are some new programming mechanisms that allow you to make something happen when something else happens, which is just like procedure call. When this call happens, this thing over here is supposed to run. Well, now, when this piece of code is executed, something else over here runs, or runs instead, or runs before, or runs after. So in some sense, you can demystify a lot of this stuff by forgetting about all of the meta-level stuff and just understanding it as new programming mechanisms, new ways of making two pieces of code integrate and compile into a binary that runs. Okay? So this is a piece of code, a little sensor class, and it has a data member signal of type Boolean and a method detect, which gets called when the sensor detects a signal, and the detect method sets the signal data member to true. Okay, so there are a couple of different join points that you could talk about in this piece of code. One would be any call to the detect method. One would be the execution of the detect method body. Here's a join point, the set of a data member. Okay, so these are join points in the AspectJ model. One can now write point cut descriptors that say, well, when the signal data member of the sensor class is set, cause some piece of code to run in an aspect somewhere. Okay. Here is, in fact, a point cut descriptor relative to that simple example. This point cut descriptor says all of the join points, and there's only one here, at which the detect method of the sensor class actually begins to execute. Okay? And there are other point cut descriptors in AspectJ. So you can talk about all calls to methods, execution of method bodies, reads and writes of data members. You can constrain the selection of join points using within. So you can say all calls within some package, all calls that occur within the dynamic scope of some other call. That is what the CFlow point cut constructor is for, and so on and so forth. Okay? And one can use pattern matching constructs in these, at this point in a point cut descriptor. So you could say public void star.detect, and that would be any execution of any method called detect in any class. Okay? Now the idea is by advising that point cut descriptor, you cause things to happen. You essentially add behavior to your system in a way that is independent of the ordinary class hierarchy. So here's a piece of advice then, building on our example. This says before the execution of sensor.detect, click a camera. Okay? So the idea here is that you want to write a piece of code that has the effect that when the sensor detects a signal, some camera gets triggered, okay, to take a picture of some detected phenomenon. So here's a piece of an aspect that would do that. Before any execution of sensor.detect, tell some camera to take a picture. Okay? And so in this way, one, in some sense, adds a side effect to the detect method, causing a camera to be clicked. And then here is the the aspect module itself that would wrap up all that code as a module construct in AspectJ. Aspect is a keyword. Sensor camera is the name of the aspect. Has data members, a sensor and a camera. Declares a point cut called detects. Detects comprises that set of join points described here, the execution of sensor.detect, and then this is a piece of advice. It says before any of these join points, in other words, just before sensor.detect executes, tell the camera to take a picture.
What is sensor S in this aspect?
This is an aspect that, oops, a little typo there. This is an aspect whose purpose is to integrate the behavior of a sensor component and a camera component, such that when the sensor detects a signal, a camera gets triggered.
I'm asking a more specific question. What's in line 2? It starts off sensor S.
That's a data member.
But it has nothing to do with the code that's up there, right? I mean, or does it play some role in this?
For a moment, think of this aspect as just a class. Okay? When you construct an instance of this class, you give it a reference to a sensor and a reference to a camera. And the point here then is that the aspect says, well, whenever any call is made to sensor.detect, assuming, okay, I understand. So, right. So we're not constraining this piece of advice to be fired on this particular sensor detecting a signal. Good observation. It's good. Yeah.
So in terms of the advice, here you got before, so that's pretty simple. I can imagine you'd have after, you know, it's sort of
There's before, after, and around.
And okay, and there's no other manipulation of sort of the structure of the source. You can't say, you know, before and then iterate over the statements or something like, you know.
No,
okay.
not in AspectJ.
So suppose I have follow up on Jim's question, 10 sensors and 20 cameras in my program. They all have different lifetimes, different scopes, things like that.
These are
How should I think about this?
These are great questions. Let me just push it on the stack, and you'll see that, in fact, one of AspectJ's weaknesses is dealing with that exact point. Okay?
Regarding what you call demystification, I mean, this very much reminds me of parallel program composition as in the 80s, right? Not only that, we now kind of talk about method calls, things like that, as opposed to signals or events being subject to superimposition, right? Would you agree, or is that too far-fetched?
I think it's okay. Okay, so let me continue. So here's where we begin, and this apropos of all of these comments. Can you come back to that at the end, and let's go back. Apropos of these comments about instances of sensors, there is actually a problem with AspectJ. This is a kind of an analysis of the relationship between classes and aspects in AspectJ. What we see are that in both classes and aspects can have fields and methods. Classes, unlike aspects, can be instantiated under programmer control and can be manipulated at the instance level. So I can say new X, where X is a class, and then I can do things with the object that I created. In the AspectJ programming model, you declare an aspect module, but you have no control over the instantiation of aspects. Essentially, the language runtime creates one global instance of that aspect module, and it advises, it's essentially kind of a type-level modification of your program structure rather than an instance-level modification of your program. I'll make that concrete in a minute. An aspect, on the other hand, unlike classes, can declare Pointcut's advice, and there's another construct in AspectJ called introduction that we can talk about later if you want. So in some sense, aspects and classes are kind of like each other, but they're incomparable. Aspects are stronger than classes in these ways, and classes are stronger than aspects in these ways. Aspects are more expressive than classes in these ways. There's something weird going on here.
Kevin?
Yeah.
I thought aspects did have static and dynamic flavors. Was that something that was dropped from AspectJ at some point?
Okay. There's a very limited capability to cause multiple instances of aspects to be created. Okay. It's very limited and very constraining. Okay. But we can put that as a footnote. Okay. Similarly, if you look at methods and advice, there's kind of a weird asymmetry. They both implement procedural abstractions. Methods are named, advices are anonymous, and they alone can be bound to the join point selected by a point cut expression. Now, in our analysis, these asymmetries and non-orthogonalities in the language design create a variety of problems. So the first kind of major point of this talk is to convince you that there's a problem here, that the difference between aspects and classes creates problems for programmers. It certainly doesn't satisfy kind of abstract notions of conceptual integrity in the design of the language. And I want to show you now concretely that it hinders your ability to do two things, to separate integration concerns and to separate what we call higher order concerns. So here's your example with multiple sensors, okay? It's just a scenario. This is an object diagram. I have three sensors, S1, S2, and S3, instances of the sensor class, two cameras, C1 and C2, and a display. And in this particular application, I want the following kind of integration behavior. When the first sensor detects a signal, I want the first camera to click and the second camera to click, and I want some other message to be displayed on some other kind of advice. So there's a kind of relationship between sensor and camera, and I have two instances of that relationship, this sensor-camera integrating relationship. And I have a different kind of relationship between sensors and displays, and one instance of that relationship. Okay, so is the example reasonably clear? When the sensor S1 detects a signal, these other things should happen on the side. Okay? A very simple, straightforward approach that you might expect from a student to implementing this system would be to start with a couple of object-oriented classes and then just to modify those classes to achieve the required integration. So to the sensor class, you add references to camera objects. To the camera objects, you add references to the sensor class. To the display, you basically tie these things together and you have them call each other. Okay, so you change the implementation of sensor detect so that when a sensor detects a signal, it calls the associated camera objects. A couple of problems with this, pretty clear. The types become tightly coupled, and we end up with scattered and tangled integration code. The code responsible for those relationships that tie together the behaviors of cameras and sensors are now scattered out over the sensor and camera classes.
So this would probably be a bad student solution, right? Because you probably would want the student solution to be using the observer pattern.
Okay, great. So the students, they first learn about this, but then they learn about the observer pattern. So then, then they produce this solution. Okay. They combine the observer pattern with the mediator pattern, and they define a sensor-camera integration kind of class. A sensor-camera object observes a sensor, and when the sensor notifies it of a signal, the sensor-camera integration object turns around and tells the camera to take a picture. Okay? And here we have the announced events, and there's some code in here to register with the appropriate events and so on and so forth. Some problems with this approach from the aspect-oriented perspective are several. First, there's still some scattering and tangling of integration concerns. Okay? If you didn't need these behaviors to be integrated, you wouldn't necessarily have to add all this event code all over the place. Okay? Moreover, and this gets to the second part of the talk, we might not have time for it, but this approach violates this notion of obliviousness that the aspect community has been so concerned with. What they want is for the authors of the base code not to have to anticipate the introduction of aspects. You shouldn't have to be aware when you're writing the sensor class that somebody might want to integrate your behavior with the camera class. Okay? So that is the aspect-oriented critique of this, your suggestion.
So, the way I view it is that simply, if you write it this way, you have to anticipate the join points, right? You actually make the join point explicit in your code.
Exactly. And if you write a paper and send it to the aspect community, and it says what you said, they'll send it back and they'll say it violates the obliviousness property because you're anticipating what aspects are needed. Now, that's where there's some difficulty with the aspect account. On the other hand, This, I think, is the big question, one of the big questions today in this whole area. Okay, so with that mediator-based approach, you could create two different instances of this sensor camera class to connect sensor 1 to camera 1, a different one to connect to camera 2, and an instance of this class to connect the sensor to an instance of the display class. And everything is nice. And we end up with a runtime object structure that looks just like this picture. Very nice. So the observation is, well, can't you do even better by leveraging aspects to do the same kind, to perform the same kind of mediating behavior, but without requiring the base code authors to anticipate the needs for integration, without having the need for all that event code? So then this is the notion, right? Here's your sensor. All you do is you introduce an aspect. There's no event code here, no signaling. You write this piece of aspect code. Before the sensor executes, you call the camera's click operation, and similarly to integrate sensor objects with the display. It sounds like it ought to work, but there are some problems. The first one that crops up is that you don't have control over aspect instantiation in AspectJ. So in fact, you can't create two instances of this aspect to connect the sensor to the first camera and to the second camera, respectively. Okay? You don't have control over aspect instantiation. Now, going to Craig's point that there is some kind of model, yeah, you can declare an aspect to be per target or per this, which means that you get one aspect instance per instance of some other class. But that's not what you want here. You want two instances of this aspect for one sensor object, and that can't be done with AspectJ's per construct.
People then put on an aspect that captures the constructor for sensor and then builds up its own tables of instances so then it can manage its own.
Perfect. That's what happens, right? Not only can't you create separate separate aspect instances flexibly, but aspects can't advise other objects selectively either. Okay? So if I say before sensor.detect, I essentially get a callback logically from every instance of the sensor class to this aspect instance, and it has to figure out where the callback came from and decide what to do with it. Yep?
So one solution you now seem to go into is, why don't you use the aspect facility simply to insert the mediator and observer pattern into the code?
Good. I'll get to that in a minute. Okay, so here's an instance level view then using aspects. Here are our sensors. Here's our sort of one global sensor camera integrating aspect. Because it advises the sensor class, it gets callbacks every time any sensor gets triggered. And it has to figure out where those callbacks are coming from. So it typically will do that by registering sensors in a hash table and doing some kind of lookup and then deciding what to do. Okay? Similarly, if the aspect advises the camera class, it gets callbacks from every instance of the camera object. Now this is fine in some cases, but if you have one list object in a 50 million line program and you want to integrate it with one instance of some other object, you don't want to advise every list object in your 50 million line program. It's not the right conceptual model, and unless you're very careful, and I don't see how to do it, it's not very good for performance either. So here's the instance of the sensor display integrating object. And now what you see is that the conceptual and probably runtime overhead increases linearly, not only in the number of objects that are advised, but in the number of aspects that are advising them. Because now when this sensor triggers, which has nothing to do with either the camera or the display, both of these aspects get callbacks. They need to do these hash table lookups, and that's the kind of world you live in. Okay? So it's really just the wrong conceptual model. That's what you want, and that's what you got. Okay? So our approach really, and this is the first half of a solution that I'll present today, is to allow aspects now to be instantiated under program control and to advise objects at the instance level. So we've introduced a notion of instance level aspects. You declare an aspect to be instance level, and now it can be instantiated under programmer control. And this is the kind of code that you can write. Here's your sensor class, no event signaling. Here's your camera class, no event signaling. You create your camera objects. You instantiate your aspects multiple times, telling them essentially to advise these objects selectively. This works. Okay? All of this is implemented as really a quite complete extension of C#. And now you end up having your runtime object model look like your logical model, and life is good. Okay? So it's all implemented in a language called EOS. It extends C#. It's as expressive as AspectJ. It has essentially every feature of AspectJ, but it also supports this instance level advising. Okay. Now, going to the question, why don't you just write your aspect to introduce the observer stuff? That is this solution right here. Okay. So in this figure, this shows the code implementing the full systems that I've described. Here's the EOS code. This is your sensor code. This is your camera code, and this is your mediating code. This is the observer approach as a student might write it. This is the observer approach where the aspect introduces the observer stuff into the base code. And I'd claim just in terms of length, which is not certainly a perfect measure, you've got sort of better abstraction here, you've got less code to write, and you've essentially just got a cleaner picture here.
Is that observer code reusable observer code or specialized to that particular observation?
It's specialized to that particular observation. Right. Absolutely. It's very special case. Okay? Yep.
You criticized one of the introducing the mediator approach for performance reasons, or just writing the tables yourself to do instance specific.
Well,
one of your criticisms.
Right. There are two costs, right? There's increased design cost.
Sure. One of them was performance.
And there's a performance cost.
And does your implementation of EOS solve that somehow?
Yeah. Okay. So the trick is that what we do under the covers is essentially introduce delegate lists at the join points that are selected by Pointcut descriptors. Okay, so you've got a Pointcut descriptor. The compiler can figure out statically which pieces of code are advised, and what it does under the covers, it introduces an observer kind of structure. Right, and then when aspects register with objects selectively, they register with the delegate lists of those particular objects. So other objects that are not advised don't. They essentially have to ask, is anybody registered? So it's a test for 0. That's where the overhead is. Rob?
Yeah, I was actually going to complain that I think your picture on the previous slide actually isn't very fair. I want you to put another color in there called compiler-generated code. And I think that the two rightmost columns would probably look pretty comparable. It's just that in the EOS case, the compiler generated a lot of the purple gobbledygook from the AspectJ prime case.
Well, it might have. I mean, the compiler, our compiler introduces delegate lists. Other compilers could optimize away some of that inlining calls and so on and so forth. The fact, Parnas basically said you modularize systems in different ways, you might get the same object code. You're saying you might get the same object code. It's true, you might get the same object code, but you've got better modularity at the level the developer cares about. Okay? So this piece is about separation of what we call higher order concerns. So suppose that you've now got your system where sensors are integrated with cameras and sensors are integrated with displays, but you decide that in some cases you want to cache sensor signals rather than updating cameras and displays immediately. Okay, so you want to be able to turn off the propagation of signals from sensors to cameras, cache them up, and maybe propagate them along later. And there are lots of applications of this kind of pattern. So one approach that you might consider taking is, well, now you write a new aspect, and what it does is it advises the sensor camera aspect, for example. So it advises around the piece of code that causes signals to propagate from sensor to camera. So when you advise around, your code runs in place of the underlying code, and you can optionally delegate back to the code that would have run in the first place. So the idea would be, write another aspect that advises this aspect, intercepts its propagation actions, and essentially caches them. It's fine. There's a problem, though, and the problem is that advice bodies are anonymous in AspectJ. So you can't write, so here's our sensor camera integrating aspect. We wrote this before the sensor detects this signal. We want the camera to click. This piece of code has no name. Okay? And so we can't write another aspect that says, around that thing, do something else. And, you know, I mean, it's kind of a dumb problem and not very deep, but it's real. Go ahead.
So how deep is that problem? I mean, couldn't I just factor myself using modular methods?
Okay, so the proposal is instead of what this piece of advice does is it simply delegates to a real method, and I wrap that other method. Turns out to be problematical, okay? Because there's all kinds of parameters that have to be implicitly passed, and you have to figure out what they are on a case-by-case basis. And if it's an around method, you have to essentially pass as a thunk the thing that you would proceed to call. You know, it turns out not to be as simple as you would think, right? So the problem is you can't say around something because the something can't be named very easily. And this ends up limiting you to a kind of an architectural style that is very pervasively in the heads of the AO folks. And the style is you write your base code and then you write your aspects. And you can't do any more than that, okay? So it's sort of, the notion is we live in a world of two-story buildings. We've got base code and aspect code.
Well, obviously this focuses on the AspectJ paradigm as opposed to other areas.
Okay, so fair, I mean, fair enough. There are people who are looking at this, but, you know, I mean, the AspectJ model certainly is, again, the most influential. And your comment notwithstanding, if you talk to aspect people, they talk about base code and aspect code. There's this two-level conceptual model of how one designs systems in this style. There shouldn't really be any difference between these two kinds of code. They ought, you know, we've got an integration mechanism. We ought to be able to use it flexibly. Yep, comment?
Yeah, so I'm concerned, you know, this two-layer thing already introduces an issue with respect to scope. So you have the aspect code that gets injected, and you refer to variables in that scope. Now that code, what are the variables referring to, right? It could be, you know, in other words, can you speak about the local variables at the join point?
You can't speak about. You can speak about some context, but not all of it. So you can speak about the object that's the target of the call. You can't speak about the local variables. You can speak about the instance, the data members of a class. You can't talk about the local data,
so
the local variables of a procedure.
In the advice code is the object that's being modified.
The object being modified, the aspect that's modifying it, the data members.
All arguments.
If
all
you
arguments.
had this three-layer building, what object would that be inserted? You know, the
third story would be advising the second story, and so it would talk about its data members.
Right, so it can never talk about the original.
Right,
object.
unless they're somehow. It's a good point. Okay, so in the approach in the EOS approach, there's only methods. Okay, named methods and a separate method point cut binding construct. So I can say, here's a point cut, here's a method. Now I want to bind this method to this point cut, so that. Instead of writing this, here's my point cut descriptor and here's the advice, I write a method instead of the advice, and then I do this binding before these join points essentially call this method. And now you've successfully done what Ralph was talking about. You've essentially got an advisable sort of aspect thing. So here now is what the overall picture looks like.
Actually, can you go back? Because
Yep.
what Ralph just said is, and you sort of replied to Ralph's question, was that there are these implicit parameters that arise in this advice. But how do I see those? I mean, this before bit set cannot be an ordinary method because it will have to have access to these special things, or is that something you bind up there?
They're passed explicitly here, okay? And there's an explicit thunk available to be passed at this point.
Okay.
Okay? So it's just...
So basically the binding chooses what of those implicit parameters you're actually going to use and pass as an explicit later to the function.
Yeah.
Great.
Why couldn't you have just done that in the other, on the left-hand side too? The body, I could just say before bit set, pass a bunch of arguments.
Yeah.
Exactly the arguments I would be saying in the call before bit set. I think it might be a good language design to force the programmer to always name these things so they always have the opportunity to impose later.
Yeah, good. Can I come back to it?
Sure.
Okay, let me just see if I can go on here. Okay, so the approach that we've basically developed then is to take this world, which is the world I described up to this point, and merge classes and aspects. And now let classes declare point cuts, do introductions, and bind methods to point cuts. Okay? So there's no longer a need for a separate aspect abstraction. There's simply an empowered notion of class in EOS, where classes can declare point cut descriptors and bind methods to point cuts. Okay? So now here is the code for our example. We have a class, and this is all backward compatible now with C#. We have a class, sensor camera, references a sensor and a camera, has a method which, when called, will tell the camera to take a picture, and then it has this binding construct that declares a point cut and binds the take picture method to those join points. Yeah.
I still don't see how you address Jim's original question about the sensor here.
Okay, so this is a piece of elided code. You declare, good, perfect. I probably left something off. Essentially, you declare this, this piece of binding to be at the instance level, okay? And then there's a provided method for essentially causing only those join points of the specified S and C objects to be advised. So you're pointing to an omission on my slide. Okay. Here's the aspect then for the third story of our building, and this shows the forwarding of the thunk. Okay. So this is the delay aspect. If delay is turned off, then so what we do is we advise around the mediator's method for propagating the effect, and whenever the mediator would have clicked the camera directly, we instead call this method. This is our delegate list, our thunk, if you will, gets passed to this method, and we write this code. If we're not delaying updates, then p.innerinvoke, where innerinvoke is a method of this delegate chain that essentially calls the method that would have been called in any case.
So should I think about these aspect classes as things I instantiate, and in the constructor I pass
S and C.
The identities of the objects which I want to.
Absolutely.
That's
yeah. And let me just, I hate slides flipping, but I'll just go back and this is exactly the code that you would have written. Okay. So in the constructor of this sensor camera object, to the constructor you pass S1 and C1, and it selectively advises the join points of those particular objects. Yep.
So the constructor has a special semantics because the binding only happens once? Is that correct?
No, you can actually bind or unbind whenever you want. So it is under programmer control in this world.
I would assume that what you do to get it specific to a particular sensor and camera is that you actually just have the point cut descriptor, the join point descriptor, say that the receiver is the S instance variable.
Essentially, that's what you're doing. There's an implicit target this construct for instance level point cut descriptors.
But there's nothing special about the constructor or the instance variables or anything like that. It's just the join point descriptor is where all that connection happens.
Right. Right. Okay. So, the contribution here in some sense is a simpler model of AOP that doesn't really lose anything. We no longer have aspect as a separate module construct in this language. we no longer have this notion even of base and aspect code. We just have modules, and they're just like old modules, except now they can advise each other. Okay? So advising basically just is now seen as another composition mechanism like procedure call. A can call B, or B can advise A. I mean, one could even just refactor code to interchange advising and procedure call if you wanted to. There's no constraint to a two-story kind of story or architecture, and there's no need really for this kind of semi-mysterious notion of aspects as somehow modular representations of cross-cutting concerns. What we rather see is that aspects are just modules applied in a particular way to modularize these sort of scattered bits of code.
The thing I don't understand that relates to the obliviousness, which seems like a good property, is that the advice is a come-from statement as opposed to a go-to statement.
Yeah.
And so, if I design my system, that example you gave with sensor and cameras where you explicitly add the observer pattern to the sensor, then when I'm looking at the sensor code, I have some feeling of that I know what that code's doing because it's deciding to go notify clients about, observers about its actions.
Right.
Whereas now, given your system, I can go ahead and grab in at any point and say, now I'm going to grab control here.
Right.
And so I don't understand how you preserve, it seems like for safety you want to preserve that obliviousness, and I don't see in here any mechanisms by which you force the aspects to allow the base code to remain oblivious of their existence.
Well, there's two problems with obliviousness. One is that if you let the base code writers just write their code the way they ordinarily would, they may not write it in a way that makes it easy to write the aspect. Okay. The other problem is that aspects can get in and do whatever the heck they want, and they can completely break the satisfaction of the specification of the object. But engineers are empowered to make those sorts of decisions. I mean, do we want programming languages telling us we can't do that? Maybe yes, maybe no. That's philosophical debate. But let me talk about this notion of obliviousness for a second. Can I test your patience by talking for just a few minutes about obliviousness, or are we finished, Jim?
You're not few. We're not finished. We have the room until noon. So
Okay. I mean, if people want to get up and leave, that's fine. I just have a couple of slides on obliviousness. So it's been a prominent notion. The idea is you want to be able to write base code oblivious of aspects. This is a quote. This is kind of the thing that the mantra of this part of the community. Just program like always, and we'll be able to add the aspects later. And this got sold in a big way to places like DARPA, right? Because they said, oh, you write the code, and now we'll add on reliability.
The correctness aspect is really good.
The correctness aspect.
That's what I want.
I mean, so my favorite sort of response is, what's the aspect going to do? Get all the buggy code in one module? That, it's easy to joke about this, but there is something interesting here, and there is something actually interesting here, and so we've tried to figure out, what makes sense here and what doesn't. Craig?
This reminds me completely of the story of oblivious superclasses are oblivious to how their subclasses are going to
Right.
go along and extend it.
Right.
And we threw that one away a long time ago. You have to design your superclasses carefully so that they can be extended well. But it's still a good, object-oriented programming inheritance is still good.
Right. So I mean, again, in that case, a good analog, because there's two issues there. One is you want to design so that you can so that you can extend easily. You want to design base code so that you can write the aspects easily. The other is that you may want some guarantee that the subclasses don't break the system. So there's some notion of behavioral subtyping there. But as OO programmers, there's no enforcement of that. But we know that if we break it, which we might well want to do in some cases, say to do fault injection, that we know what we're doing. Okay. So if you do oblivious design, this is kind of the process. This is actually a little model of a system of a refactoring of an overlay network system that some of my students and I did. Here's the base code. These are the modules, the main modules of the base code. Then we wanted to add aspects for protocol events and logging and various sorts of aspects. If you take the oblivious approach, you write the base code first, and then you write the aspects. The aspects then depend on the base code. And here's some of the problems with this design strategy. Sequentiality. You have to write the base code before you write the aspects. If you want to get to market fast, you'd like to have these people writing their code at the same time. Okay? It's just parallel development is impeded by this notion of obliviousness. You end up dealing with complexity because the aspect writer has to understand the base code in order to write the aspects. There's an absence of abstraction. And they have to conform to arbitrarily ugly base code. And finally, because the aspects depend so heavily on details of the base code, they're fragile. And when the base code evolves, the aspects are subject to be broken. So this approach, we believe, is not particularly optimal for time-to-market dependability, avoiding late integration crises, or for managing long-term life cycle costs.
The EOS approach has, of course, exactly the same problems, right?
The EOS language does nothing about this. Okay? You need a new idea. You need a new idea. Okay? And that idea is this. The contribution of this piece of the work is in this notion that we call join point interfaces. Okay? It's just an instance of information hiding, but it says that you have to put interfaces between the aspect code and the base code. These interfaces, though, are not typical procedural or API-like interfaces. Rather, they're what we call join point interfaces, or JPIs. And what they do is they constrain the base code writer to write code to expose certain join points in certain ways. And they license aspect writers to assume that those join points are exposed in the right ways. Okay, so they define points at which aspects can advise. They can impose some additional semantic constraints. And what's really interesting about these JPIs as opposed to APIs is that they're cross-cutting. So I can write a JPI, for example, that says, across your entire system, if you want something to be loggable, you have to implement it in the following particular way so that my Pointcut descriptor now matches it appropriately. Okay? So these JPIs are cross-cutting and non-hierarchical. So instead of this picture, this is the picture you get. You interpose these interfaces between the base code and the aspects, and everybody depends on the interfaces in sort of the typical way. So the cost of this approach is that you pay some cost to define the interface, and you also incur some opportunity cost in limiting the design space. These, the base code authors are, in fact, constrained to implement these JPIs, for example. But you get benefits in all the ways that you would expect by modularizing your system. So it's a little ironic that the core approach of the aspect community is non-modular in the sense that aspects are not decoupled from base code. And this approach basically addresses that problem. So that's pretty much the end of the story.
Yeah, so one of the problems with aspects, and I don't know if your extensions address this, is that inherently when you apply one aspect A and you apply another aspect B, you don't really know about the end behavior because you have no guarantee about the orders in which.
Okay, so I mean, AspectJ and also EOS provide some mechanisms for, constraining the order in which advice runs. There are rules about how different aspects apply at a shared join point. So I differ. There is actually some control. That being said, it's not so easy necessarily to reason formally about everything that might happen.
Yeah, I mean, the problem is it's like with function composition, when I have F compose G and compose H, I sort of know I have a very nice compositional semantics, and I think
this is more like sequential composition than function composition. I mean, that's kind of what the semantics gets down to. First you do this piece of code, and then you do this piece of code, and then you do this piece of code.
Right, well, this is fine as long as all the advice is just reading data and not writing, but as soon as you have, as soon as you're inserting assignments here, and the aspects are somewhat, decoupled, but maybe they're writing, common data, it seems like this is just a self-modifying code where you just don't know what the
but you have the same problem with the observer pattern, right? I mean, this is not unique to aspects. And, my view of this is you pay something, which is the inability to necessarily know exactly what the behavior is when the piece of code you're looking at runs, but you gain something as well, which is potentially much better modularity in your code base and in your overall design process. So it's a power tool. It can be used, it can be abused. If used in the right way, then you mitigate the risks and you get the benefits.
Has anybody done a study to see that it really is a benefit over, saying doing the observer pattern or things? I mean, I just haven't seen any sort of analysis. It seems very intuitive that there's all this code that cuts across all the stuff, but is this really a better way?
I think people are still arguing about that when it comes to OO as well.
I don't think so.
Well, they are, really. Right, it's tough. I agree. I mean, it's very hard, really, to evaluate these design strategies. You do have, sort of people voting with their feet to some degree, which, I mean, herd mentality isn't always the right. It doesn't always give the right answer. But I mean, it looks to us that there are some cases where, in fact, you're better off. It's not clear to me really how far you can push this. So I think I think the jury is still out.
When you criticize two-level design, you could have a hierarchy. So base code, first-level advisors, second-level advisors, third-level advisors, and so on.
Right. That's hard to do in AspectJ, but not in EOS.
Right, but you chose to make everything flat, right? There's no built-in hierarchy in your language.
The question is, what kind of structures can you express in each of these languages? In AspectJ, you are largely constrained, again with a footnote, to express two-level structures. In EOS, you can express n-level structures without doing anything out of the ordinary.
You don't impose this
No.
levels.
No.
Well,
I mean,
what is the rationale for this choice?
For not imposing these levels? Essentially what we've done is we've reduced AspectJ to the addition of a new composition mechanism to the language. So in addition to function call and event notification, you now also have advising. And in EOS, you're not constrained to use that in any particular way. You can build arbitrary advising structures. So in just the way that you can build arbitrary call graphs.
I understand, but one advantage of hierarchy would be that you reason about base code. Then you reason about base code
Okay,
in the first
sure.
level.
Okay, absolutely. So we don't do anything to prevent engineers from doing that. And they're probably well advised to do that in most cases.
My question also had kind of to do with this issue of structure and level. So if I write in a device that says insert this logging thing at every call anywhere, right? What happens to it? Does it advise itself as well?
Yeah. So your point cuts typically say on any call to any method, not within, not exclamation point within, and the name of the aspect itself, output the trace message. Okay. So you use the point cut composition language to exclude, to basically
That's
to.
already the case in standard AspectJ.
Yeah. Yeah.
And
So
within as a C flow you're going to be using to make sure when it calls the standard library, it's not tracing all the calls to string concatenation.
Yeah, absolutely. You can do that. Exactly. Right. So you can basically say any call to any method within the library that's not within any call to any method in the library. And in that way trace all top-level calls to the library, but not any that are below that. So, it does, at least with respect to some of these sort of concerns, it does give you kind of an interesting kind of expressiveness. Again, I think the jury's still out on this, but there's enough excitement about it and enough mystery and enough controversy that it seems to make sense really to take it seriously and to try to understand what's there. Maybe last question? No, we have until noon. I'm here, so I just don't want to test your patience.
So I'm curious. I've seen a bunch of presentations that have examples and inserting various logging kinds of things. It's a very common example.
Right.
I'm curious what sort of real code that uses aspects looks like, both in terms of the actual descriptions, the point cut descriptions, and the the size of the aspects themselves. I mean, so logging, you can see it's going to be a few lines of code, right to a file or something like that. But for sort of non-obvious, types of aspects, how complex do they get, I guess, in real code?
It's a good question. So in developing and trying to test this notion of join point interfaces, we took essentially a 50,000 line program, which is laughably small around here, but it's still a real program. It manages ad hoc overlay networks. This is Jörg Liebeherr's hypercast system. It's a really interesting, nice system. And we picked it as a kind of a case study for comparing and contrasting different AO strategies because, in fact, the code base embeds some of these classic cross-cutting concerns. And there are a couple. There's a bunch of logging code scattered out across the system, number one. Number two, it used the observer pattern to allow clients of overlay nodes to register to be notified when certain events happen in the overlay. We thought, well, we would want to replace that with some notion of advising those actions rather than registering for events. And there were 3 or 4 other sort of concerns that were scattered out across the code that we decided we'd like to try to modularize in AspectJ. So the first thing that we did in this study is we just pulled all the code for those concerns out of where it was, put it in aspects, and essentially tried to figure out how hard would it be to write the aspects if the base code had been written just as it was, but without all that cross-cutting stuff in it. Okay? Here are 3 point cuts that we ended up having to write, in some sense, to cause the code that we had been pulled out to be put right back in from where we had taken it. This point cut, for example, I don't know if you can read it back there, says, any set of some stuff and you're within some code and, there's a variety of things sort of going on here. It's quite complicated and ugly. Okay? And that's the problem with obliviousness. If you let the base code author write the base code however they want, the aspect code author is stuck with having to write these complicated point cut descriptors to describe where they want their advice to go back into. So this gives you a little sense of what some point cuts might look like in a system like WebSphere. Okay, so IBM's WebSphere has apparently been heavily aspectized. And there are a bunch of other kind of enterprise software people out there, JBoss and others who are pretty heavily committed to this technology and are building application servers and that sort of thing using aspects. Spring is another big one. And this is the kind of code you see. Now, if you have this notion of a join point interface that constrains the way in which the base code is written, then you can end up expressing all of this stuff sort of more like this because there's some regularity in the base code. There's just a uniform way in which certain kinds of events are signaled by the way the code is structured. There's no extra code in there, so there's still this sort of quasi-notion of obliviousness. But it's much easier for an outsider to say, I want things to happen at these particular points.
So is it true that if I just change the name of a function, I can have a point cut fail?
Absolutely.
So as a writer of the base code, I actually have to know exactly what the point cut descriptions are in all the aspects when I change any name. Is that correct?
Absolutely right.
Okay.
That's right.
Until his
What?
Until his work.
Right. I was going to say, yeah, the JPI. Okay, yeah.
Right. And as an aspect writer trying to advise code that was written by some oblivious programmer, you may have to write 40 different point cut descriptors because they're inconsistent across the base code. So here, there's a classic example in the aspect community of the figure editor. And basically, the idea here, it's much like my example. You've got points and lines, and the idea is that when they change, some aspect is going to update a display. Here's what we think these JPIs sort of look like today. the JPI says, here's the syntax. Well, a couple of things about these JPIs. First, you define the scope. You say the constraints imposed by this JPI only apply to the figure element class and its subclasses. Okay, so if you're in a 50 million line program, you don't want everybody to have to conform to this JPI. So the JPI says, I only apply to these elements of the base code. Here's the syntax. Okay, change signal is a point cut that matches any execution of figure element set or of any method of any subclass of figure element that starts with the name set, or the execution of any method of any figure element class that is called move, or that starts with the word move. Okay? And the constraint that this JPI imposes on the base code designer is here. That change signal, this point cut, is satisfied if and only if by and only by those actions in the code that signal transitions in the abstract states of figure elements. So this basically says, as the implementer of any figure element object, if you're going to do something that changes the state of a figure element, it has to be done in a way that matches this point cut descriptor. And the only things that you can make match this point cut descriptor are those things that satisfy this predicate.
But that's just a convention, right? There's nothing that the language enforces.
Well, no. I mean, at this point, it is a convention. So it's interesting in AspectJ that there are some, and in EOS as well, there are some limited mechanisms for doing certain kind of checking. So you can, in particular, you can write point cut descriptors, and any place where they're matched, the compiler will give you an error message. Okay, and you can use this to do some limited checking of these kinds of JPIs. And so this is an example that essentially uses built-in constructs to check in a limited way that that these JPIs are actually enforced. So I think that the broader, the bigger answer is, yeah, write checkers, or do verification, have people inspect code, do testing in general. But more particularly, there are some interesting opportunities to use AspectJ or EOS itself to do some of this checking. So let's see if I can decode one of these. So this right. If you go back and look at the constraint, one of the things that you want is that for a piece of advice not to call a mutator of the thing being advised. Okay, that's a non-interference requirement. So this piece of code right here basically says signal an error if there's any call to any of the mutators of figure element class in the dynamic scope of any call to any method of the figure element class. Okay, so a mutator is going to cause advice to run, and you don't want the advice then to turn around and call any of the mutators of the object that caused the advice to run. So this is basically a dynamic check of a non-interference requirement for this kind of JPI. So that gives you some sense of, I think broadly speaking, you're on your own, but you can develop tools and checkers and other stuff to deal with that problem.
All right, wait.
Yeah.
I think this is a good point at which we can thank the speaker. Anybody wants to talk to him, just say that.
Thanks, Jim. Thank you. Thanks for having me.